Hello and welcome to Mr. Linford's math course. In today's discussion, we're going to be introducing the topic of exponential functions. We're going to differ from some of the work we've done previously with functions by really diving in heavily to this specific type of a function. We're going to first define what it is, and then we're going to explore the various graphs of exponential functions in hopes to better understand them and better understand how to apply them when solving real-world application problems. Now first, what we're going to need to do is have a definition of what an exponential function is. I'm going to define an exponential function as a function of the form f of x equaling b to the x power, where b is a part of the real numbers. Remember, this little symbol right here, it looks like a C with a tick mark in the middle. Sometimes people think of it like an E symbol. This means is a part of, or it sometimes means is an element of. This is just math shorthand to let you know that whatever number we have here is just some real number. Remember, real numbers are any number on the number line. So what are some examples of exponential functions? An example of an exponential function might be f of x equaling 2 to the x power, or it could be 3 to the x power. Maybe it could also be something like a half to the x power, or the square root of 2 to the x power, etc. Remember, we are saying b here has to be a real number. I'm going to put a couple more qualifications on this definition in just a little bit. But what I first want us to do is to take a little bit of time, and I want us to explore the graphs of exponential functions. I want us to take a look at what's going on visually as we set up this type of function. I'm going to go ahead and use Desmos. And what I'd like you to do is, as we explore Desmos, try this graph on your own. And I'm going to have it linked down in the description, and it's going to be on the course website. But what I'd like you to do is play around with this graph. You can recreate it if you'd like, and try to see what you notice about the setup to the function and how the graph is altered based on that. So let's take a look at Desmos here. All right. Here is our graph. You'll see we have the coordinate plane and we have this red line representing our function. You'll notice that I've graphed this function here marked in red. That's f of x equals b to the x power. Now what Desmos did was I put what's called a slider here, a slider on the b value. What that means is I can click and drag this circle, and I can move it around, or I can slide it around to see what the graph would look like as I change b. So we start with b equal to 1. So this is 1 to the x power. Take a minute and jot down, what do you notice about this particular graph? What do you notice about it? Take a look at the graph for yourself, move it around, slide around on the graph, zoom in, zoom out, but try to get an idea of what's pictured here. You can even tap on the graph, get it highlighted, and you can click on various points. And you can move these points all around the graph and see what you get. So take a minute, jot down what you notice. All right, now what I'd like to do is I'd like to alter the b value. I'd like to play around with the slider to see what the graph might look like. So I'm going to take the slider and I'm going to increase b. Let's take the b value and increase it. What do you notice is happening here? As I drag the slider around, What's happening to B? I started at 1. Oop, careful, right about here. And now, right about there. And then I started dragging it. I'm starting to increase the B. What happens as I increase B? Write down what you notice about the graph. All right. Now that we've taken a look here to see what happens as we increase B, we have this rather unique shape to a graph, something we haven't entirely seen before. Now let's go back to 1. Let's set B to be a 1. I'm going to try to get that very carefully. There we go. So this is where we started. We just increased B. Now let's decrease B. Let's drag it to the slider to the left. Let's say B is 0.6 or 0.7 or 0.3 or 0.2 here. What do you notice now about the graph? Again, move it around. Take a look at it. Zoom in. Try to get a picture of what's going on, okay? And write down what you notice. All right, before we move on, let's keep decreasing the B value. Let's keep playing with this slider. We had it set equal to 1, and we increased it from 1. We even moved it up to a 10 value here, and we can see what happens. We then set it back to 1, and we said, you know what? We just saw what happens when we increase. Let's start decreasing. So I'm going to keep decreasing 1. And then what happens when I get to 0? Take a look here. Did you see what happens? There's 1. This is all these decimals. And then as soon as I hit 0, what happened to the graph? It's right here. You can still see that faint red line. All right. At 0, what do you notice about the graph? And then, what do you notice when I make it a negative number? What's happening? Where did we go? So what I'm going to do right now is I'm going to hit play on Desmos, this little play button on the side here. And what it's going to do is it's going to run through all the various numbers for B. It's going to plug all these numbers in, and we're going to see what the graph looks like. Maybe I'll zoom in a little bit here, and let's take a look. We can see the graph come into play. We see it bending upwards, then we see the other side bending up, and then it disappears. Did you notice that? It's almost as if it gets erased somehow. Right there, it disappeared again, and there, it pops back up. So, what I'd like you to do, try and explore this graph and record down what you notice about the graph as we have B equaling 1, as we have B greater than 1, as we have B being less than 1, and when we have B be less than 0. What do you notice about all these individual points? Let's go ahead and let's take a look at what's going on here. So let's go ahead and let's define all that we notice from these various situations. Well, first, what do we notice when B is equal to 1? That's this case, when f of x equals 1 to the x power. What do we notice here? Well, I'm going to change colors. I'm going to say that the graph is a horizontal line. That means that we had the equation, the graph is y equals 1. Or you could say the graph is f of x equals 1. It's a horizontal line at the height of 1. And why was that? Well, that should actually be fairly obvious to us. Plug any number in for x, and what do you get? For example, plug in f of 5 here. What's 1 to the 5th power? Oh, that's just a 1. And let's plug in maybe negative values. Let's plug in a negative 2. What's 1 to the negative 2 power? Well, that's 1 over 1 squared, and oh, that's just a 1 again. So when b is equal to 1, your output will always be 1. When b is 1, you will always get a 1 out, because 1 to any power is just 1. That should be fairly obvious to us, okay? 1 to any power, you'll always get a 1 out. So you're going to have that horizontal graph. Now let's take a look at what happens when b is greater than 1. When b is greater than 1, you'll notice that we have this unique shape to the graph. It's almost as if the graph, we could say, is curving upwards fairly rapidly. So this is how we're going to describe the graph when x is greater than 1. When x is greater than 1, we are going to say the graph curves up to the right. So it curves up to the right very quickly. Okay? As we move over to the right-hand side, the graph keeps increasing and increasing. We can see that if we look at the graph right here. As I move along the points, you'll notice that I start jumping up higher and higher and higher very, very quickly. In between 0 and 1, I just jump up, like, let's see if I can see that, 0.9 of a value. But between 4 and 5, I jump up a whole lot of points, don't I? So, as we have b being greater than 1, we keep moving upwards to the right very, very quickly. Now let's ask ourselves what happens when we were between 0 and 1. So let's get a little small decimal here, something like 0.8 or 0.7 or 0.3, for example. What do you notice in this case? Well, you should notice that we have the opposite graph. When b is between 0 and 1, we will say the graph curves up to the left. So no longer are we curving up to the right, we're curving up to the left. And why is that? I wonder why that is. Let's take a look here at an example. We have the value of 0.3, or you know what, let's set it to be 0.5. I'm terrible at getting the Desmos slider to be exact. Okay, 0.5. As I plug in bigger and bigger values for x, I get smaller and smaller and smaller numbers. But as I plug in these negative values, I get bigger and bigger and bigger numbers. Why is that? Well, let's see what's going on here. Let me go ahead and make this little example. F of x equaling 0.5 or 1/2 to the x power. Okay, let's plug in a number for x. Let's take 1/2 to the 4th power. 1/2 to the 4th power is a half times a half times a half times a half. So that would be, if we do that 4 times, that should be 1/16. That's a very small number, isn't it? Every time I multiply small decimals or fractions by each other, I get smaller and smaller numbers. Okay, so that should make sense why we're decreasing as we increase x. Our outputs are decreasing. But what happens when I plug in negative numbers? For example, let me plug in, let's do a -4 in this case. Well, keep in mind, when you have negative numbers in the exponent, that means you have to flip it. So this is really 2 to the 4th power, which is a 16. So this is why when I plug negative numbers in for these small fractions, I end up flipping them, and I end up getting bigger numbers. So hopefully you can see why when I plug in negative values, I get really larger quantities for the output. Like, for example, when I plug in -4, I end up with Let's see if I can get that very carefully. I end up with a 16. Did you see that? When I get -4, I end up with 16. But if I plug in a 4, you'll notice that I end up with a 16th, which is it's hard to get it exact. 0.063 is just about 1/16. So you can see why this is working. When I have negative values, I'm increasing, but large positive values, I decrease. So that's what happens when I'm between 0 and 5. What I'm really curious about right now is what happens when b is 0. When b is 0, notice where the graph is. It's right here on the x-axis. When b is 0, all that we get is a 0. And shouldn't that make sense? What's 0 to any power? 0, right? But notice that my graph doesn't start on the y-axis. It doesn't start beyond in the negatives. It actually only is in the positive numbers. Remember, I can't take 0 to a negative power. That's not allowed. Now, the other weird case is, what happens when b is a negative number? Like, let's set it to be a -2. So b is a -2. All right, close enough. Now, when it's set to -2, I don't have a graph here. For any negative number, I can't see what's going on. It's not graphing. So why is that? Well, if I had, let me get some space here. If I had anything less than 0, if I had a negative number, so let's say I had f of x equaling -2 to the x power. What would happen in this case? Let's plug in values for this. And you know what? I'm going to clear some space here so we can see what all's going on. So here we have the example f of x being -2 to the x power. Here I've picked a b value that was less than 0, something that was negative. Let's set up a table for input values x and output values for f of x. And I want to see what we get as we plug in different values. So let's plug in something like 1. What's -2 to the first power? Well, -2 to the first power is just -2. Easy as that. Now let's plug in a 2. -2 to the second power is +4. Then let's plug in a 3. -2 to the third power is -8. If we plug in 4, -2 to the fourth power is 16. What you should notice happening here is that we don't have a continuous graph. Instead, we are bouncing around the coordinate graph, the coordinate plane. So let me set up values here. Let's say that's 2, 4, 6, 8. 2, 4, 6, 8. 2, 4. So I'll set these values in place. And let's try to plot these points. When x is a 1, we're at -2. When x is a 2, we're at +4. When it's 3, we are at -8. So somewhere down here, if it would let me draw down there, somewhere right here. Okay, close enough. And then when it's at 4, we're up at 16. So that's at 2, 4, 6, 8, 10, 12, 14, somewhere like way up here. So sometimes students think, oh, you should be able to then connect these points, and that's what the graph would look like. Well, actually, it doesn't. Let's plug in other values. Plug in something like a half, right? Let's take x being 1/2. So what is negative 2 to the 1/2 power. Well, that's actually not a real number. Remember, you can't take the square root of negatives. So, and that, well, you can, but it's not a real number. So, what we have here is in between these points, numbers don't exist, or coordinate points don't exist. We have what's called a very discrete graph. A discrete graph is a graph that's not continuous. It's more so a collection of points. And that's what we have when we take negative numbers to exponents. The trouble is that we keep bouncing around positive, negative, positive, negative, positive, negative. And when I try to take roots of them, it doesn't work. I need complex numbers to do that. So what I'm going to do is I want to go back to this definition right here. And we're going to define an exponential function as a function of the form b to the x power, where b is a real number, and I'm going to put this little note to us here that says b must be greater than 0. You can see b could be greater than or equal to 0, but in our class, we're not going to deal with it when it's 0, that really kind of odd case. We're going to deal with numbers that are greater than 0, okay? So we're not going to have this weird situation with negative b's where the points bounce around on the graph. Instead, we're just going to have the normal types of graphs that we were seeing, these continuous curved graphs. So let's take a look at our graph here of our parent function, and let's define a couple key terms. When talking about exponential functions, we can talk about what's called exponential growth and exponential decay. Exponential growth is the result of increasing output values f of x. Remember, f of x is like y here. That's your output. So exponential growth is when you have increasing output values for increasing x values. Another way of saying this would be, as x increases, so does f of x. So that's the idea with exponential growth. Let's get a picture of that. That's when, if we had a little graph of this, exponential growth occurs, and let me maybe adjust it a little bit here. Exponential growth occurs when we're increasing as we move to the right, okay? That's exponential growth. And you know what, let me even try to draw that a little better. Let me have a little more dramatic of a curve here. There we go. That's exponential growth. As x increases, so does the output. The bigger the x value, the bigger the output. Now, the opposite can be said for exponential decay. Exponential decay is going to be the result of decreasing output values f of x for increasing x values. So that means as x increases, f of x, the output, decreases. You get smaller and smaller numbers. So if we were to graph that, that's the situation where as x increases, the numbers decrease. So this is what exponential decay looks like. So growth you're increasing over time. You're increasing as x increases. Decay, you're decreasing as x decreases. What were these situations when this occurred? Let's go back to Desmos. This is an example of exponential growth. When was it that we had exponential growth? Well, hopefully you noticed that's when we had b greater than 1. When I had numbers bigger than 1, I had very dramatic growth. And in fact, as I kept increasing, the curve got steeper and steeper and steeper, way and way more dramatic. When did I have decay? Let me drag the slider around and let's see. My graph was curved downwards when I was between 0 and 1. When I had those small fractions and decimals, that's when I had exponential decay. That's when, over time, as x increases, the points decreased, and they decreased quite a lot. So let's go ahead and record this down. For exponential growth, this is when b is greater than 1. For exponential decay, this is when b is between 0 and 1. These are important concepts to understand because the idea of exponential growth and exponential decay is something that's going to be very important to our later applications. Now, continuing to look at this parent function of the exponential function, let's talk about its domain and its range. Remember, the domain is, I'll put a little note to us here, the set of all x values in the relation. And the range is the set of all y values in the relation. So as I look at all of the individual coordinate points, if I had a list of all the x values, that's the domain, and if I had a list of all the y values in every coordinate point, that would be the range. So let's go back to Desmos and let's take a look. Play around with the graph. I'm going to change the slider here so that way we don't deal with negative numbers. We stop at a 1. So I can do that by just tapping on the slider, and then I can click off for it to be set. What I'm going to do is I'm going to hit play. And I'm even going to zoom out a little bit here. What do you notice about the graph? Well, one side we keep curving upwards while the other side goes off to the left. The other time we curve up to the left while the other side goes flat out to the right. What do you notice about the domain? Let me pause it at a certain point, maybe right about here. The domain, remember, we had the little trick. The domain is how far left and how far right does the graph go. Well, obviously, the graph is going to keep going off to the left forever and ever and ever, right? No matter how much I move over on the graph, I'm now over in the negative 800s, the negative 900s, the negative thousands. You can still see that little red line keeps moving over to the left. Okay, so I know that the domain is going to keep going off to negative infinity when I have this exponential growth. But what about the right-hand side? The right-hand side, as I move upwards, it almost looks like it's going perfectly straight, but wait a minute. You can see, oh, it's just slightly, ever so slightly, keeps curving over to the right. It keeps moving over the slightest amount. So hopefully you're saying to yourself that the domain of an exponential growth function is negative infinity to infinity. We keep moving over to the left towards negative infinity, and the right, though it's increasing, though it keeps increasing, we keep moving over to the right more and more. Slowly, but we do keep moving over to the right. So this domain is negative infinity to infinity. Does that change when we have negative numbers? When I have an exponential decay? Well, let's take a look here. This time, the right-hand side obviously is going off to positive infinity. The more I move over to the right, you can see that that red line is still moving over. It keeps going to the right forever and ever. So obviously the domain is shooting up towards infinity when I have a exponential decay problem. But what about the left-hand side? Well, hopefully you can see that the left-hand side keeps curving over to the left more and more and more. As it increases, it still keeps moving over ever so slightly to the left. It keeps expanding outwards. So again, the domain is negative infinity to infinity. That should be pretty obvious to us. When we look at this parent function and we ask ourselves, what values can we plug in for x? Well, you should say to yourself, you can plug in whatever you want. You can take any of these positive numbers to any power you want. X could be negative, it could be positive. You know how to take negative exponents. You just move the number to the other side of the fraction line. You know how to do positive exponents well. You could even have fraction exponents, right? You've worked with rational exponents in taking roots of them. So really, you can plug in any number you want for x. So the domain of an exponential function will always be negative infinity to infinity. Okay? No matter whether you're increasing or decreasing, whether you're exponential growth or your exponential decay, the domain will always be negative infinity to infinity. Now let's take a look at the range. Let's go back to our Desmos graph. I'm going to hit play on the slider here, and notice the range. The range is how far up and how far down does our graph go. Well, if we take a look at an exponential growth situation, we keep increasing forever and ever. We keep shooting off towards positive infinity. So obviously our range is going to go off towards positive infinity here. But how far down does our graph go? Well, if I click on these points, it looks like it gets to 0. Right about here, we're at 0. So do I hit the x-axis? Do I have an output of 0? Let's take a look. We're going to zoom in, and I'm going to keep zooming in. What do you know? As I've zoomed in, I'm actually not on the axis. I'm very close to the axis. I'm at like 0.00189, and I keep getting closer and closer to the axis, but I never actually hit it. Let's take a look over here at maybe like 5 or something, or -6. It looks like maybe I'm on the line here. But if I zoom in, and if I zoom in enough, you can see again, nope, I'm still not on the line. I'm incredibly close to it, 0.00062. I'm incredibly close to that line, but I never actually hit it. So ask yourselves, is it possible for our output to be 0? Is it possible for f of x to equal 0? Well, that means, can b to the x power ever be 0? For example, could 2 to the x power ever equal 0? Or could a half to the x power ever equal 0? Well, hopefully you're saying to yourself, no, there's no way for this to be 0. 2 to any power is going to give me either decimal values or whole number, or very large numbers. It will never give me 0. What's the only way to get 2 to be 0? Well, that's if I multiply it by 0, but that's not the case here. So this can never work. And this could never work. Try it. Pick any number. Pick any positive number. Pick like 5. 5 to what power gets you 0? Well, 5 to the 0 power, oh wait, that just gets you a 1. So there's no situation here where I can have some number to an exponent get us 0. So this is going to mean that our range gets incredibly close to 0, but never actually hits the line. We never have an output of 0. It gets incredibly close to it, but is never actually at 0. And then the other side is going to go up towards positive infinity, and it's going to keep increasing. So one side, when we had exponential growth, went all the way down to 0, never actually hit 0, but kept getting incredibly close to it, while the other side shot up towards infinity. So hopefully you can see on the graph here that situation take place. But this is for exponential growth. What about exponential decay? Let me get into a decay situation. And what do you notice here? How far up does our graph go? Well, obviously this side on the left here keeps increasing towards infinity. But the right-hand side is now the one that shoots down towards 0. It never gets to 0, but it gets incredibly close. It keeps moving closer, little bit each time. It never actually hits 0, but it's almost there. So we can say that the range for any exponential function that you have will in fact be 0 to infinity. So the domain for every exponential function is negative infinity to infinity, and the range for any exponential, no matter what number you plug in for b, will be 0 to infinity, 0 not included. Hopefully this is making sense to you. You can play around with the graph and see that you're never actually hitting 0, and you're always increasing forever and ever, and you're always moving out towards the left and the right forever and ever. So you can see how these domains are set up and these ranges are set up. Now, I want to talk about some of the key points and some asymptotes that we're seeing here in the graph. One thing that we should notice is there is an asymptote anytime I have an exponential function. The asymptote, remember, is we can define it as an area of space where the graph is undefined, where the graph does not meet the qualifications. For us, an asymptote is going to be a line that the graph never hits. It's a line that the graph will never hit and will never cross. As you see the exponential functions moving around here, is there a line? Is there a point or an area on the graph that this curve will never cross? Can you see a line that the graph gets incredibly close to but never crosses? All right, well, hopefully you're noticing that every time I graph an exponential, no matter how I structure the curve, we always have this situation where I get incredibly close to the x-axis. I keep getting incredibly close to having a 0 value, but as I zoom in, I never actually hit the axis. I keep getting incredibly close to the axis, but I never actually hit it. This is going to be the asymptote for us. The x-axis, or I should say the line y equals 0, is going to be our asymptote. So our asymptote here is going to be the x-axis, which is the same thing as y equaling 0, or f of x equaling 0. That's the equation of that line, the x-axis. So, same thing. Now, are there any key points that we notice on the graph? Again, let's play around with the slider, and let's see if there's any unique points that pop up. So I'm going to hit play again on the slider. And what do you notice about the graph? As it changes, do you see any key point anywhere on the graph? Each time it looks like the graph keeps altering. It keeps bending upwards one way and then upwards the other way. But what is staying the same every time? Hopefully you're noticing this dot right here. Let me stop the slider. That point, 0, 1. This point, let me hit play again. Let me go somewhere else. I'll hit pause. There I go again, 0, 1. This point, whether we're on exponential growth or let's set up a decay, 0, 1. This point always exists no matter what the exponential function is. So let's list that as a key point. A key point here is the coordinate 0, 1. And why is that? Why is this a key point? Well, let's plug it in and let's see what we get. Let's take f of 0. So I have b to the 0 power. What's any number to the 0 power? That's just 1. Oh, that should be fairly obvious to us. That should be obvious why this is a key point for any of those functions we were graphing. Okay, that makes sense, because anytime I take any number, whatever number I plug in for b, anytime I take it to the 0 power, it's always going to be a 1. Okay, that makes sense. So we have this situation. Here's our special asymptote, the x-axis, and here's our special key point. We always have this y-intercept here of 0, 1. Now, I think it's important for us to also take a look at some unique points that appear when we alter the graphs. By this I mean, as we either increase b or decrease it to get exponential growth or decay, we want to see, is there any particularly unique setup that we have that allows us to determine how narrow or how wide the graphs actually are. So let's zoom in a little bit and let's see what we have going on. So I'm going to zoom in on the graph and let's set b to be a 2. Let's work with whole numbers here. So b is a 2, okay? And let me zoom in just a little bit more so we have individual components. Okay, take a look at this graph here. And let's take a look at all of the coordinate points that we have. So we have 0, 1 as our intercept. We also have 1, 2. And we have, it's going to be hard to see, but let's see if we can get on the graph right here. That should be a 2, 4. Okay. So we have some interesting values here. That should make sense. When I plug in 1 for x, I have 2 to the first power, and that's just 2. So that coordinate point makes sense right here. 1 and 2. If I could ever get it. There we are. Now let's change it to a 3, and let's see what happens. Let me reposition the graph here, and let me change b to 3. Okay. Now, what do you notice? Well, obviously, we're more narrow. We're increasing a lot quicker. So we still have the same intercept, but now we have the point instead of 1, 2, we have 1 and 3. Now let's change it to 4. As I change it to 4 here, I still have the same y-intercept, but now I have 1 and 4. What you should be noticing here is that anytime I plug a 1 in for x, I get the point of b out. What I mean by that is, let's take f of x equaling b to the x power. Anytime I plug in 1 for x, I just get b out, right? Because anything to the first power is just itself. So if I had, let's say, f of x equaling 2 to the x power, and let's say I plugged in a 1 for x, I would just get out a 2. And let's say I had f of x equaling 3 to the x power. And again, for x, we just plug in a 1. Well, we're going to end up with a 3. So what are these as coordinate points? As x is 1, the output is 2. As x is 1, the output is 3. So for our standard example, when x is 1, the output appears to always be b. Whenever you plug 1 in for x, you seem to always get out what the b value is. Let's see if that works for decay as well. Let me get into a decay situation here. Let me set b to be, something like 0.5. So I'm at a half here. So b here is a half. Let me go to 1. And very carefully, when x is 1, hey, our output is 0.5. So we still get the same value. And in fact, I wonder what negative 1 would be. Negative 1 actually gives me 2. If you can see that very carefully. Oops. Let's get it right about there. So negative 1 for a half would get me 2. And positive 1 would actually get me to a half. Now, again, if I was at positive 2 for b, I would have 1 getting me 2, and I would have negative 1 getting me a half. Let's see if I can see that here. There we go. So, knowing what happens when x is 1 and x is negative 1 helps me kind of determine the shape of the graph. I can know relatively how narrow or how wide it is. So what we can say here is that this is going to be pretty standard as a key point for us. Now it's going to vary with each time I change b, but for any b, there will always be the point 1b, okay? Anytime you have a b value, whatever it is, you will always have the point 1b. And you might be able to argue something about when you have negative 1, you would end up b to the negative 1 power, but we don't need that necessarily. We know what the intercept is, and we'll know what a specific point are. So these are some key points that we should know. The intercept for every exponential, and a point for specific b values. Now let's go ahead, and I want us to try exploring a couple different example problems where we look to see what happens as we alter the b value. And let's see if we can determine some unique features that they're going to have. Let's take a look at these 4 functions. What I want us to do is, before we go ahead and actually plot these using our calculator or Desmos, I want us to decide by just looking at the functions, can we tell if the function is exponential growth or decay? Can we identify its domain and range? And can we identify the asymptote and any key points that the function might have? So what I'd like you to do is take a couple minutes, try to organize these. I did it by color coding. You could label these graphs differently. You might call this one f, this one g of x, this one k of x, this one h of x, whatever. You can do it any way you'd like. I just did color coding because, well, I like color coding. But go ahead and organize these by what type of exponential you're dealing with. Okay, first up, we should notice the difference between growth and decay. If I have an exponential growth, that means the b value, the number I'm taking the exponents of, is greater than 1. So the green function here, because it's a 2, and the blue function here, which is a 5, those are both exponential growth. They're going to be increasing as x increases. Now the decay occurred when the number I'm taking the exponent of was between 0 and 1. So the fraction 1/2 and 1/5, those are going to be exponential decay. As x increases, they're going to be decreasing the function values. Now, what is the domain of these graphs, and what is the range of them? Well, you can ask yourself, domain, are there any numbers you can't plug in for x? No, I can plug in any number I want. I can plug in negative numbers for x. I can plug in positive numbers. I could plug in 0. I could plug in fractions or whole numbers. It's all good. So the domain for all 4 of these graphs is negative infinity to infinity. Now, what about the range? What about the range of these graphs? Well, hopefully you notice that the range here is still going to be the same. 0 towards infinity. No matter what you plug in for x, you will never get the function to equal 0. It's not going to happen, no matter which function you use. Any one of these, you'll never get it to equal 0. So that's why we start at 0, not including 0, and then we're going to increase towards infinity. Whether we're increasing on the left or increasing on the right, we're going to keep shooting up towards infinity. Now let's talk about the asymptotes and any particular key points. Well, you should notice that all of these satisfy the definition of a standard exponential. So the asymptote would be, what values can you never achieve? What outputs can you never have? What area of the graph can your curve never cross? Hopefully you're saying that's the x-axis, because we just got through saying there's no way for a function output to equal 0 here. There's no way that these exponential functions will give you a 0. So that's why the x-axis is really going to be our asymptote. It's not going to work. And now key points. Before we had the key point 0, 1. Was that a key point for all of these? Well, by quickly testing, yeah, in fact it is. Take any of these values and raise it to the 0 power. Anytime you raise any of these values to the 0 power, you always get them to equal 1. Now, while it's important that we know that the key point of 0, 1 is a part of every graph, we're in fact going to know that that's the y-intercept, we also should probably know another specific point to the graph. In fact, a point that helps us determine how wide or how narrow the graph is going to be. So again, pause the video and take a minute to try to determine, for all of these given functions, what is at least one other point that they will all, what's at least one other point, I should say, that each of them have specifically that would help you determine how wide or how narrow the graph are. Take a minute, pause the video, and try to determine those points. So for me, what I did was I went and I plugged 1 into all of these x values. By plugging in 1, I know automatically what the output's going to be. It's just going to be the b value. So for the first function, I plugged 1 in for x to get 2. I then went into the next function and plugged 1 in for x to get 1/2. This is done repeatedly because it's very easy to tell what something to the first power is. Now, I could also say, well, it's pretty easy to determine what something to the second power is, but as I keep increasing the power, it's not always easy, right? Like, what's 1/5 to the 7th power? Oh gosh, well, I'd have to try to figure that out by multiplying 5 to the 7th power, and it gets a little messy. By knowing that first coordinate point that's off of the origin, I can pretty accurately sketch what that graph might look like. So here are some specific key points. You could have also done some of the negative versions. For example, you might have said for the first function, you could have plugged in a -1 and gotten 2 to the -1, which is 1/2 value. You could have plugged in -1 for the next function and gotten 1/2 to the -1 power, which is 2. And you could have done that if you wanted as well. That would give you a third point to be able to work with sketching the graph. That might also be helpful to you. But generally speaking, these points, knowing the first one off and knowing the origin, will be fairly helpful. So with these key points understood, we're able to really picture the graph, how wide or how narrow it would be. We also understand how to limit the graph by the asymptote, what values it won't ever have but approach. We're able to see the domain and the range of these individual functions and how it compares to the parent function, and we can tell which functions show both growth or decay. What I'd like us to do now is go back into Desmos and look at each of these four graphs individually. Let's observe how they show either growth or decay, and let's see how these key points are adjusted and how the domain and range are featured in them as well. So I'm going to unclick this box. So I'm not worried about graphing these parent functions anymore. Instead, let me graph what we have here. So we have f of x equaling 2x. Then we have 1/2 to the x power, 5 to the x power, and we have 1/5 to the x power. You'll notice in each of these cases where there is decay and where there is growth. You can play around with this. I have the Desmos graph linked in the description. You can play around with this, take a look, move the graphs around, make sure you're comfortable with the domains and the ranges, but also make sure you're comfortable seeing what all is going on here. Let's now go and explore an application problem, and in particular an application problem that's one of the most common uses to exponential modeling. Carbon-14 dating is a method for determining the age of something that is made up of organic material by using the properties of a particularly radioactive isotope of the carbon element. Now, I think it's first important that we understand what organic material means. Now, organic material is a type of, we could say it's a type of matter that is largely produced by a carbon-based compound. So I would say the majority of it is made up of some carbon building blocks. So think of living organisms like animals and plants as being organic materials. And there is this particularly radioactive isotope of the carbon element that's called radiocarbon, carbon-14. So, using the fact that when an organic being dies, it stops exchanging carbon with the environment. That's an important idea. So when a living being dies, or I should say when an organic being dies, it no longer exchanges carbon with the environment. So it's capped off. And the total amount of radiocarbon, which we call carbon-14, begins to decrease as the isotope undergoes radioactive decay. So two key ideas there. One, when the organism dies, or when the being dies, it stops exchanging carbon with the environment. So its amount of carbon is capped off. Then, its amount of radiocarbon in particular begins to decrease. It undergoes this particular decay. Using those two ideas, a researcher can use a sample of organic material, whether it's a piece of wood or a leftover bone, whatever, to determine when an organic organism died and how old it is. So the older a sample is, the less radiocarbon there is left in it. So if you took a bone or a piece of wood or some organic material and you analyzed the amount of radiocarbon that's left in it, knowing how much there would be to start, you can guess how old it would be. So for radiocarbon, carbon-14, it has a particular exponential decay function. And this is how we're going to define that exponential decay function. What we have here are a couple key elements. One of the things that we have is called A sub 0, or A naught. This component right here is the initial quantity of radiocarbon. So that's how much radiocarbon you start with. So whether this organism was some animal, whether it was some specific type of plant or tree, whatever, it's going to have a certain amount of radiocarbon it starts with when it immediately dies. Then it will start to decrease from there. And it decreases over time. So T is the time in years that it's been dead. So that's how long it's been since it died, whatever the organic being was died. And it's measured in years. Altogether, we get this response that tells us the amount of radiocarbon you are left with, okay? How much you're left with. So we might be able to measure how much we're left with, and if we know how much there was to begin with, we can probably estimate the amount of time it took to get to those levels. So let's go ahead and let's try to look through some application problems using this particular function. Now, let me remind us that the function, the exponential function for radiocarbon was a sub 0 times 2.718, and then the exponent was a negative 1.2 times 10 to the negative 4 power times t. So let's take a look at how we might be able to use this function to solve for radiocarbon in a couple different examples. So in this case, suppose you start with 300 grams of radiocarbon. That's our initial amount. That's the a sub 0. So a sub 0 here is 300 grams. And suppose that this particular organism has been aging for 2,000 years. So time is 2,000 years. It's a 2,000-year-old organism. What you need to figure out is how much is left. Well, you know A0 and you know time. You're now trying to figure out what A of t is. So let's go ahead and let's plug these values into the function. Let me clear some space here, and let me see if we can fit in this problem. A of t is equal to, well, a sub 0 is 300 grams, and we are going to multiply that by 2.718 to the negative 1.2 times 10 to the negative 4 times t, which is 2,000. So we're multiplying this number in scientific notation by 2,000. Okay, you're going to need a calculator for this. Let's start with the exponent, okay? We have 300 times 2.718 to the, all right, let's start with 1.2 times 10 to the negative 4 power. And, oh, that's negative. And then we're going to multiply that by 2,000. I'm getting that we need to take 2.718 to the negative 0.24 power. Well, if I take 2.718 to that power, and then I multiply that by 300, I'm going to end up with, I'll move it over here, 235.99 grams. This is how much radiocarbon we're left with. We know the starting value, and we know how long it's been decaying for. So this is how much we're left with. You should notice that not very much has gone away over 2,000 years, right? If we started with 300 and we're down to roughly 236 if we round up, we've only lost 64 grams over 2,000 years. That's why this is really beneficial. Radiocarbon decays very slowly. So we're really pretty good at estimating ages based off of it. Now in the next problem, let's say the sample was aged for 6,000 years. We're still using the 300 grams, but now we're going to say it's been 6,000 years. So let's take A of t, and let's say, okay, you got 300 grams, and you're going to multiply that by 2.718 to the negative, let's see, that's 1.2 times 10 to the negative 4 power times 6,000. By the way, when you have really complicated functions like this, which most real-world application problems will have, do them in parts. Don't type everything in your calculator at once. I don't know why students do that. They try to cram everything into their calculator. You end up actually taking up more time making sure you've used parentheses properly than if you actually just typed it in parts. So let's start with the exponent. We have that 1.2 times 10 to the negative 4. Actually, it's negative 1.2 times 10 to the negative 4. And I'm going to multiply that by 6,000. Okay, when I perform that multiplication, I end up getting the exponent to be negative 0.72. So let's take 2.718, and we're going to raise it to the negative 0.72 power. And then, well, I guess I could write down what that is. When I do that, I get long decimal, but it's 0.4867885947. Okay, something like that. And I'm going to multiply that by 300. When I multiply that by 300, I get 146.04 grams. This is how much is left over after 6,000 years. We still have quite a bit of radiocarbon left over, okay? Again, what's important here is knowing what information you're given. We've been given the A of 0, we've been given the A of t, and we're able to figure out what's left over. Now let's go ahead and take a look at the next problem. Let's say the sample has aged for 5,730 years. That seems like a very specific number. Let's figure out what we get for this, how much radiocarbon is left over, and let's try to see if we can identify what's so special about this year. So A of t is going to be 300 times 2.718 to the negative, let's see, 1.2 times 10 to the negative 4 power times t being 5,730. All right, we're going to do the same thing as before, and let me clear the space down here. Let's start by figuring out what the exponent is going to be. What is the exponent on 2.718? So negative 1.2 times 10 to the negative 4 times 5,730. I'm getting negative 0.6876. Now let's take 2.718 and let's raise it to that power. I'm getting 300 times 0.5028171435. I like to use a lot of decimals here. Do you have to? No. It's probably just as good to round to like the thousandths place, maybe 3 decimal points. But I like to use quite a lot of decimals, especially because when it comes to round-off errors, I want to try to minimize that as much as possible. So let's multiply that by 300, and we're going to get 150.845 grams. Okay, nothing different about this problem, but what's so special about this year, the 5,730? What's so special about that? It gave us roughly 150 grams. Well, this is what's called the half-life. This is called the year that gives us the half-life of radiocarbon. It's how long does it take for the initial amount of radiocarbon to be cut in half. So I will say that this is the half-life. And it turns out it takes about 5,730 years for us to cut it down to about half of what it started with. Again, this is why this carbon dating or this carbon-14 dating is so incredibly helpful. It takes a very long time for all of the carbon to really be breaking down. So we can utilize that to really help us out. So that's what I had for us to explore for today. It's a helpful idea, something you're probably going to cover in science classes. But if you have any questions about any of the work that we've done, in particular our work on interpreting the graphs of exponentials or even applying and working with the functions itself, please let me know. My email is klinford, that's KLINFORD, at wccnet.edu. Let me know if you have any questions or comments or things that you'd like to go over. And until next time, take care.